So I thought I would just focus on radar for a little bit first here, where there's actually some precipitation occurring. I wanted to use Charleston's radar because there's a lot of rain falling right now in Charleston, West Virginia's area, and moving up to the northeast from there. So this is a reflectivity. In other words, it's sending a pulse of microwave energy out, and some of that pulse returns. The radar listens. It listens a lot, about 90 those echoes of showers and all to be coming back to the radar. And so when it sends it out, it listens. Also, interestingly, the radar sends a beam out in one direction. The antenna tilts with time. It can go all the way up to 19.5 degrees. So that energy going out at each of those levels as it's going up. Of what the three-dimensional aspects of radar are. All you're seeing here right now is the maximum reflectivity, and the fact that it goes to 19.5 degrees, it stops at different levels along the way. So you actually are scanning about 12 different levels during that time. All happens in 6 minutes. You get a complete scan all the way around in 360 and up through the vertical. So let's look at this. Notice to the south of Charleston, there's some darker shades, even some yellow. There's heavy precipitation coming down there. So what that means is that precipitation there is returning an echo stronger than the precipitation further north. So that's all you're saying here, is the echo is a stronger return. So the precipitation is heavier. You'll notice with time that flash flood watches have gone out, or warnings actually have gone out across parts of that area down there. And you can see the area the heavier rain is in, and they're forecasting ahead of time that more and more is coming to that area, so more flooding is possible. There's an interesting thing happens with radar. Mountains block. If you have a sign there from Charleston, you'll notice there's not any echoes. Why is that? Well, that is because there's a ridge in direction. So we don't get a good return if you're in Charleston along that little line right there. So that's just one product, though. Let's see if we can get. I will look at base velocity next. Base velocity, what we're doing with that is when we send a signal out, we know the frequency of that signal. So when it comes back, it will come back at a different frequency depending on how those particles are. Look at that base velocity here. There we go. Coming up now. Moved me to into Louisville. But if we don't, I can still show you it here. Because you'll see you go from green to red. Green is air that's moving towards the radar. Red is air that's moving away from the radar. So all you're looking for is you look for where the wind velocity indicates 0 and all. So let's see if we can do this here again. Maybe a little better this time. But I wanted to show you here because you can really see a 0 velocity on this radar. And you'll notice the scale is down here in the bottom left. And with that zero velocity, if you look at it where it is, think about putting a wind perpendicular to it. In other words, coming straight in at 90 degrees to it. That is the direction of the wind speed. And by knowing that, we can do that in tiny little areas that actually indicate how strong the wind is in different things. So I don't think we're going to get this right now, so we'll move on to some other stuff. But there's you'll notice the winds. Notice the zero velocity line is kind of east-west at the bottom. So that means the lower level winds are moving from the south to the north. And then it turns to more north-south. So that means the upper level winds are moving from the west to the east. So you can actually get a three-dimensional picture of it. There's a couple other products here that are interesting, but the way we've had some issues here with the things working, I'm not going to try to get them. One product determines precipitation type. That's from Dual Pole. Beam of energy. By knowing that what they're looking at from the vertical and the horizontal, you can able to depict the two-dimensional image of a precipitation or particle. By the way, rain looks another, hail would look different. All of that gives us an indication of, oh, this is where the hail is, this is where the rain is, the snow is. And today, if you were to look at Charleston's image, you would see that the precipitation higher up, where the angle is higher in the sky, was all snow. Down low, it's all rain. And because we can indicate the size and the intensity of the precip, we're also learning that we can calculate the amount of precip. So that's the other estimate we're getting out of the radar today. How much rain has fallen? And we can look back upstream from other radars and see, oh, this is how warnings based on projected rainfall. So that is a good first estimate of all the fun stuff you can do with radar. Let's get out of that for a minute. We'll close this out here. So I wanted to bring up precipitation. So clouds and precipitation are kind of interesting and important. We've learned that clouds impact temperatures. We've learned precipitation is kind of important. We might want to know if it's going to rain on me or snow on me. So let's look at this as a slideshow here. We'll move through it pretty quickly, actually. How do clouds form? We talked about moisture reaching saturation in the atmosphere. Water vapor reaching saturation and condensation begins. Well, unfortunately, it's not as simple as that. Water vapor is invisible. There's always water vapor in the air. It's invisible. When you see a cloud, there must be some raindrops there or little tiny cloud droplets. Interestingly, something is required to make a cloud. It's dirt or sea salt or some other different things that are called cloud condensation nuclei. Why do we need these? Well, we need these because a raindrop is much, much bigger than a cloud drop. So when the cloud drop is so tiny, everything we've done talking about relative humidity has been based on a large, flat area, all relative humidity being the same over it. Now we're going to introduce a curve. When you introduce a curve, things change. In other words, the steeper that curve, the more it's curved, and the tiny little raindrop has a heck of a curve. A tiny little cloud droplet has even more. What you wind up with on that cloud droplet is the condensation, little particles of water don't want to hang around there anymore. And it's much, much easier on a curved surface for that water droplets to dissipate, go out into the world, go back into water vapor. So that's where the condensation nuclei comes in. What that does, it allows that little tiny water droplet from a cloud to stay together. And because it does that, it allows that droplet to gradually grow. So where it doesn't need those dirt condensation nuclei as much, and eventually it gets up to the size of a raindrop. So you can see the exact same thing I've just told you here looking at that curved surface. These nuclei vary from every part of the country. If you're in the Midwest, there's going to be a lot more dust. If you're along the East Coast or the West Coast, it's more salt from the ocean. But they allow these little tiny raindrops in the cloud to form. And by forming, we get the clouds. So, guess what? There's the same process for ice. These little raindrops, little tiny cloud droplets, don't freeze unless the temperature gets way, way, way super cold. So how the heck do we get snow and ice out of these clouds? Well, we get it because there's a similar little tiny particle of dust. They're called an ice-forming nuclei. And they begin to work at about 16 degrees Fahrenheit, minus 9 Celsius. All of a sudden, if there's that little bit of dust in it, it will allow ice crystals to form in these droplets, and we wind up beginning to form ice crystals throughout the cloud. However, water can be super cold. So that is a thing because of the kinetic energy in the water, it keeps that growth of ice from forming. All right, we haven't talked a thing about how precipitation forms, but I'll tell you right now up front, almost 90% of all precipitation forms as snow, especially in our latitude, may even be higher. Even down in the tropics, probably 50 to 60% form as snow. Now, any snow or ice particle or water is going to have what they call a terminal velocity. So, if you were to go outside and drop a feather, it would only go at a certain speed all the way down to the ground. Why is that? Gravity's pulling on it. Wouldn't it keep getting faster? Because gravity is a force that causes things to accelerate. No, friction is also working on it. And the same happens with these particles. That's why clouds, none of the precipitation is coming down to the ground initially, because terminal velocities for these little tiny droplets that are in the cloud are very, very, very low. So they wind up staying in the cloud because the air is moving up. We keep these droplets in the cloud. So how do we form rain that gets big enough to come to the ground? Well, there's two processes. Collision coalescence is one, and the other one's Bergeron-Findeisen. Where we live in the mid-latitudes, collision coalescence mainly occurs in the summertime or in the bottom of the cloud, sometimes in winter, but not a lot. Almost all precipitation is Bergeron-Findeisen. Why is that? Well, collision coalescence occurs when temperatures are above freezing, and most of our clouds are not. They're warm cloud processes. What happens? Let's take a look at that. You have a little tiny droplet, and bumped into another droplet, got a little bit bigger. All of a sudden, it's starting to fall. And it's hitting other droplets as it's going down and collecting those droplets into itself and growing and getting bigger till it finally says, I'm big enough, I can fall all the way to the ground. And it does. That is how collision coalescence works. Temperatures must be above freezing. Got to be a lot of rain cloud droplets in the thing. And these are some of the most efficient processes for giving heavy rainfall. Bergeron-Findeisen. Now, that's a little more complicated. So, what happens? You get an ice crystal that begins to grow. Well, why would it continue to grow after that? It's not hitting other raindrops or anything. Well, there's a key factor here. Let's go back one, I guess. And the key factor is that over ice, because it's solid, the vapor pressure, the saturation vapor pressure, is a slight bit lower than over a liquid. Again, we're talking pressure, so think about it. The pressure is going to move from where the higher pressure is to the lower pressure. We've talked about that. So in this case, these little water vapor are going to move away from where the liquid is towards the solid. So the solid is going to grow, and with time it's going to dominate. So that's why there are more and more ice crystals and more snowflakes developing, and the snowflakes keep getting bigger till they eventually can reach the ground, or fall down, melt, become rain, and reach the ground as rain. Virga is just precipitation that evaporates on the way down to the ground. So here are some of the possible precipitations. Rain, drizzle, little tiny droplets, generally do not amount to anything. Rain is more. And, all right, here is the different forms of snow. I want you to look at one thing. If I'm forecasting snow for your house, should be easy, right? Oh, you're going to get a half inch of liquid water. I know that normally the ratio is 10 to 1. Therefore, you got your 5 inches of snow. Easy, right? Well, what if I told you that dendrites, look into between -10 and -20, you see these nice crystals, nice and big and fluffy. Notice how much bigger they are than every other flake you see there. But all this snow is going to come from dendrites. Oh, that 5 inches might go up to 8 inches. The fluffier the snow, the higher the accumulation might be. So part of what a snowfall for you is I am also forecasting the shape, which one of these might be more likely to be occurring. And here you can see precipitation starts as snow, hits a warm layer. I showed you a sounding the other day where the temperatures were above freezing, just above the surface. What happened was the snow was coming down, hit that above freezing layer. Doesn't take a lot to melt snow. It melts, goes back down. If the temperature stays above freezing, it's all rain. Normal, right? If the temperature goes little bit below, maybe the bottom 500 to 1,000 feet, it's below freezing. Well, all of a sudden I'm getting ice, freezing rain. Not fun. Or if it's a little thicker, I might be getting sleet. Or if it's hardly any that's above freezing, above the air, I'm getting snow. So you can see how understanding the three-dimensional view of temperature makes a big difference in precipitation. Here is a classic freezing rain sounding. We talked a lot about radar already. Only thing I really wanted to focus on was just give you a tornado on the ground here. Notice here by Marion, Mississippi, that there's very strong echoes coming right at each other, it looks like. But what it is a very teeny tiny circulation in the air called a tornado vortex signature, or TVS. And next to that, you can see what they call a tornado debris signature. That is because dual pole can pick up shapes. What it did was detect things that couldn't be rain, couldn't be snow, didn't make any sense to it. So what it says was, these must be some kind of strange objects. And those objects are debris that's in the air. So literally, it is picking up the debris from that tornado. Also, there's a mesocyclone in this storm here that's making a curve like this. And that is part of where the tornado occurs from. So these are all aspects of how we use tornadoes and how we use radar. And here you can see the dual pole vantage with a hurricane. You can see the eye, wind speeds, and all of that there. Eventually, we may get to phased array radar. Phased array radar costs a little bit over $1 billion per radar. To cover our country, you would probably be looking at 150 billion at least, just for the initial outlay plus continuing. Phased array is wonderful. I've used it out in Oklahoma City. All it does, where I told you that the other radar moved up, tilted upwards with time, and back down, and sent pulses on different angles. Phased array does it all at once, so I get a complete and detailed scan of the whole atmosphere everywhere in instantly. And because of that, I can detect the tornado maybe 10 minutes earlier. Maybe I can get the amount of rainfall a little bit more accurate. All that information could be useful, but you got to justify the cost too. Here is just an estimated rainfall from one storm. We're going to talk about clouds too. I'm going to ask you this week to look at clouds. I like to look at clouds. I like to know why that cloud's there. So look at cirrus clouds, wispy clouds, stratiform, layers, cumuliform, puffy. See what you can see. Here's some coming off of a lake, for example. And here's some that are vected off of in the water or formed over the water. I had that this past week when I went across the Monitor Merrimack Memorial Bridge Tunnel. All of a sudden, there was no visibility going across the water because the water temperatures were such that they cooled the air that caused fog to form. So that's what I wanted to talk about today. Let me know if you have any questions about all of this.